I am with Wes Waite, who is part of our service department and is our instructor extraordinaire. So without further ado, I'm going to turn it over to Wes.
Thank you, Liz, and welcome everyone. This week's edition of our webinar is going to center on reading a system and where in a RF distribution system is the best place to, or best places to take measurements, meaningful measurements when setting up or troubleshooting an RF distribution system. So, first we'll discuss the most practical places for an RF distribution system measurement. And that really depends on a couple of questions. Are we initially setting up, building the system, or are we troubleshooting an existing system? Because they can be different locations for meaningful measurement depending on what we're trying to achieve. But either way, there are locations in the distribution system that should always be measured, and other locations that don't really necessarily need to be measured all the time or for every check. Before we get into the actual measurement, though, we do need to know some other things. First of all, we need to know the distribution layout. We need to have a distribution design on hand with the system laid out, telling us what equipment is in place, what level readings should be, so we have something to compare to. That's basically a blueprint for our system. Whether we're building the system or troubleshooting the system, we need something to follow to be able to properly take measurements and compare them to what should be, so that we know if we're getting good readings or not. We also need to know the specifications of all the components within our system. Some of those specifications include the coaxial cable that we're using, what is the loss structure of the coax cable itself, the splitters, what their loss factors are, the taps or directional couplers. We have a tap port loss, then we also have a through line loss for those taps. So depending on where we're taking measurements, we need to understand what we should be measuring at those points. And then finally, one of the major components of a distribution system is amplifiers. Amplifiers is one of the few things we can control, we can adjust, but we need to understand how to adjust it, why to adjust it, and so we need to understand what its amplifier is doing, what the gain of that amplifier is, and what the rated output level or the specified output level per design is supposed to be. Okay, all of these, plus any other components that are in the system that I may not have mentioned. Coaxial connectors themselves have very, very minimal loss, talking about less than 1/10 of a decibel per connector. So we typically don't account for every connector in the system, but there can be other components in the system not mentioned here, such as ground blocks or other things that may incur a loss in the system that we need to account for. Otherwise, our readings will be off. So here we're looking at a couple of the different specifications of the components I just mentioned. This is one of our splitter series, the SCVS and SXRS series. And the splitter loss is the specification that we're going to be most concerned with. You can see the frequency range at the top line there, the second line, is rated out to 5 megahertz to 1,000 megahertz. So that's what the splitter device is designed to pass signal-wise. Now, if we're designing a system for 550 megahertz as the highest frequency, or 750 megahertz, or what have you, 860 megahertz, we need to understand that so that we design for the appropriate range block of frequencies in our design. And that should have been done at the design stage prior to installation. But we need to ensure that that's been done so that the correct loss factors are in place here for the devices. So for example here, an SXRS2 has 2.8 dB of, whoop, I jumped the gun there, has an SXRS2 two-port splitter at between 500 and 860 megahertz has 3.8 decibels of loss. And let me see here if I can get my pointer up here. There we go. So 3.8 decibels of loss through that two-way splitter between 500 and 860 megahertz. If we step up to 1,000 megahertz, we have up to 4.2 decibels of loss. So if you have several of those in a system, you can accumulate quite a bit of loss there through these components. So you need to understand and keep track of the losses through the components. Now, similar to a splitter is a directional coupler or a tap. Similar being that it's a passive device, it only has loss, it does not boost up the signal in any way. But it's a multi-port device. This chart is for a single port tap. So it has an input port, a tap port, and a through port. This guy across the top shows the tap values ranging from 4 to 30 decibels of loss. And you can see the through line loss or the insertion loss rows here are the specs that we're going to be interested in. So depending on what the tap value is of this device, let's say, for example, we select a 20 decibel tap and we're running a system that's 860 megahertz at the high frequency. So we would expect about 1.1 decibels of through loss on the through line port that would be going on to the next tap location. Now this tap also has the tap down port, which would have the 20 decibels of loss based on the tap value here of 20. So these other values, these other specifications on the chart, they do tell us stuff, but for the purposes of design work and troubleshooting, primary specs that we want to look at is the tap values and the through line losses. Sometimes on the charts they're called insertion losses. But those are the specs we want to look at, and again, based on the frequency range that we're running. Then comes the cable itself. So the coaxial cable. This chart here has been around for years, as long as I've been at Blonde Tongue, over 25 years. So this is a typical cable attenuation chart. This is based on an average of cable loss specifications on what we consider the top 3 cable manufacturers in the US. That would be Times Fiber, CommScope, and Belden cables. There are other appropriate quality cables out there, but these are just based on these 3 manufacturers. So for RG6 cable, these are losses per 100 foot of cable. For RG6 cable, we're typically going to look at the low frequency range. 55 megahertz is the start of channel 2 in a cable system. So we typically look at that loss factor for the low side. And then if we're running an 860 megahertz system, for example, we're also going to look at the high frequency side loss. You can see that there's quite a difference, about 4.5 decibels of difference loss between the low frequency and the high frequency. So throughout our distribution system, we do need to make calculations for both the low frequency and the high frequency, assuming everything in between falls in between those numbers. But we need to account for the minimum amount of loss we're going to have, the low frequency, and the maximum amount of loss we're going to have, the high frequency. So anywhere in the system, we're going to take at least 2 measurements, low and high frequencies. Based on the cabling we have here, we see RG11 cabling is a larger cabling. Channel 2 loses just under 1 decibel. 860 megahertz, channel 135 loses about just under 4 decibels of signal. So you can see a larger cable loses less signal. Lower frequencies lose less signal than higher frequencies. Okay. But if you're using something other than these main 3 cable manufacturers, I would suggest finding the specs for your particular cable and just comparing it to, if it's within a couple tenths of a dB up to a quarter of a dB within these numbers, then that's fine. But anything more than that, I would suggest, for accuracy's sake, I would suggest using the specs for the particular cable that you're running. Okay, so now that we have all of our passive components, the cable, the splitters, the taps, we have the specifications, the losses for those. Now we need to look at the amplifiers. Like I said, the amplifiers are the device in our distribution system that we can control, we can adjust, and so we need to pay special attention to the specs on these guys to ensure we're adjusting it correctly. So the 3 main things that we want to look at, 3 main specifications we want to look at are the frequency range, to make sure we've got an amplifier. Now we do have, Blonder Tongue does have amplifiers that are specified below 860 megahertz. We have 550 megahertz, 750 megahertz amps. I just couldn't fit them all onto one slide. I'm just looking at the 860 megahertz and the 1000 megahertz amps here. So the frequency range of the amp, make sure it covers the channel loading, the number of channels that you're running. The gain of the amplifier is essentially based on what your input level is going to be. If we look at the output level of these amplifiers, here we have the first 2 are 30 decibel gain amplifiers. Their rated output is 3644. Now they show 2 numbers there because we typically set the amplifier outputs at what they call a positive slope. So we have 36 dBmV out on the low channel, channel 2, and we set the high channel, channel 130 or channel 135, 860 megahertz, we would set to 44 dBmV. That creates for us a positive 8 dB slope. So it helps compensate for the way that the cable slopes or tilts. So we see that we have a 30 dB gain amp with a rated output of 36 over 44, but we also have the 43 dB gain amps that has the same exact output, rated output 36 over 44. So that's telling me that they're looking for different inputs. If they're both rated, specified with the same output level, but they have different amounts of gain, then the only other difference is going to be the input to that amplifier, to those amplifiers. So on the left side, the 30 decibel gain amplifiers, looking for, you can see on all the way over here on the left, high output level minus the gain will give us our minimum input level. So my high output level 44 minus my gain of 30 44 minus 30 gets me to 14. So this amplifier, in order to achieve a 44 dBmV on my rated output, I would need to hit this amplifier with a minimum of 14 dBmV of signal. And it's typically recommended to go into that amplifier as flat as possible, meaning all channels the same level. So here we see on the 43 dB gain amps, again, the same rated output level, 36 over 44, 44 minus 43. We can hit this amplifier with a +1 dBmV and still achieve the 44 dBmV output. So the 43 dB gain amps do not necessarily get us more output level. I think that we'll save the rest of that conversation for another time. I could spend the whole hour on just talking about amplifiers and the what's and whys, but we'll just leave it at that for now. So the 43 dB gain amps take a lower input level and are typically used for the first amplifier from a cable feed. Cable company can give us down to a 0 dBmV signal, so they typically don't. They typically give us somewhere between 0 and 3. So that's perfect for a 43 dB gain amp. And then beyond that, anywhere else in the system, we're going to use a 30 dB gain amp to make the most of our levels and minimize the amount of noise we add into our system. So anyway, the frequency range, the gain, and the output level, and thus figuring out from the output level and the gain what the input level is, those are the most important specs for amplifiers that we need to look at when designing a system, when troubleshooting a system, to know how things should be set up. So now, here we have a sample distribution design. We have our head end here with a BITA 55A30 amplifier. So based on the model name, I can tell that is a 55A, tells me it's 550 megahertz. That's what that amplifier is rated for. So a 750 megahertz signal is not going to make it through that amp. I know that the system is designed for 550 megahertz. This is a 30 decibel gain amplifier, so it's got to have a minimum of 14 dBmV in to achieve that 3644 dBmV output. Then I go through just glancing through, I see a two-way splitter after the amplifier. Going down to the right, I see a four-way splitter, and then these other symbols with the 16s and the 12s, those are single port taps, tapping off signal to televisions as I go down a hallway or something, 75 feet apart from each other. At some point, I get to a location where I need to re-amplify that signal to continue down the hallway. So I see I'm running into an amplifier with about 14.7 at the high end. So that's probably another 30 decibel gain amp. Boost up to 3644 again and continue on down the run. Now, if I see I have my design considerations on the right side here too, RG6 cabling, the insertion losses of my different tap values and so on, and what my minimum signal, that's a specification that's typically specified for the project, the minimum signal level out of the taps to feed to the televisions. For an initial installation, I'm primarily going to look at my head end output, my amplifier inputs, my amplifier outputs, and my first and last tap ports on each segment. The segment being between amplifiers. So on the first section there, I would look at the 16 tap and the 12 tap. On the second section there, I would look at the 30 tap and the 6 tap. Over on the left side, just look at the 20 and the 4. And if those numbers, those measurements fall within about a decibel or so of the calculated measurements, I would say the system is pretty tight and in good shape as far as as far as the health of the system. And you should not need to take measurements beyond that. Now, for troubleshooting, we've got an existing system and we have issues. Then we're going to start with a known good location, which could be the head end, it could be an amplifier output, what have you. Then we have the trouble location, whether it's the tap port, the tap input, tap output. We're going to look at actives, any other amplifiers that are in the system. And then we're going to have the distance between a known goods location and a trouble location. I'll dig into that a little bit, just a second here. So going back to looking at the initial installation. So first off, I'm going to look at my head end output, verify that's position number 1 here on the chart. Verify that my head end is set up properly. I have the appropriate output out of my head end. If I don't have the right starting signal level, how can I hope to accomplish a balanced system through my distribution? Then I'm going to look at my amplifier input to my next amplifier. If I've got the correct components in between, the correct cable distances in between, I should come within a decibel or so of the calculated measurements, calculated signal levels in for the input to that tap. Then I set up the amplifier outputs. When you're on initial setup, if you've got a system and they don't have a source up yet, or you know, they say, oh yeah, just install the system and fire everything up, but we don't have the input signal yet from the cable company or what have you, it's really not a good idea to leave amplifiers running with no input. Either get a little rack of temporary modulators or something, just to have some kind of signal running through it. Doesn't have to be a full complement of channels, but it's not a good idea to run an amplifier with no signal into it. It can damage the amp over time. So setting up, and of course all these measurements have to be taken with live signal applied to it. So we're at amplifier outputs, we're balancing, setting up the second amplifier here, making sure we have 36 dBmV on the low channel, 44 dBmV out on the high channel, and then we can move on. We move on to the first tap port after the second or subsequent amps. So for every segment, if we have multiple amplifiers here, every segment, every amplifier, we would do the same thing. Look at the first tap port after it and the last tap port after it to see if we get close to, again, within a decibel or so, get close to the calculated readings that we should have. And I say within a decibel or so because field strength meters, spectrum analyzers, they all have at least a tolerance of plus or minus 2 dB. Our $30,000 engineering grade spectrum analyzers from Hewlett-Packard that we have in our labs have a tolerance of plus or minus 1.5. So the tolerance, you know, allowing for a dB swing either way really should be 2 dB from the calculated, because that's how much a meter could be off and still be within spec. Okay, and let's not forget to finally document all of our levels. Yes, we have a map, we have a layout of the distribution system here with readings on it that were calculated. But now let's say, okay, let's put down, annotate on the back side of the page, whatever. Location 1, the actual reading was 3643.5. At location 2, the actual reading was, 15.9 and 14.8, whatever. So, and so on and so forth. So that 6 months down the road, a year down the road, when we come back for our monthly maintenance checks, or, we come back for troubleshooting, we know, hey, okay, this is the way it was designed, but this is the way it was actually built. There was a little give and take here on the build of it. And so I know now if I come back and see that something's off by, several decibels, then that can be a problem. But if it's off by half a decibel, it's not necessarily an issue. Okay, so it's good to always document. And again, if we come back for troubleshooting, document that as well, what was changed, what was fixed, what have you, so that there's an ongoing log of the health of the system. Makes things much easier as different texts come through the system, as times change and we wind up monitoring or supporting multiple systems. It's tough to keep all of that information inside, so I need to have it all written out for me. Okay, where am I at here? Oh, so initial installation. Now, if we've got, if we had issues with, say, input 2, location 2, the input to the second amplifier, I may then go back and check positions 4 and 5 again on this small segment just to verify if I had proper readings there prior to continuing on until I got the correct readings at the input to my amplifier. Okay, so the same system now, but it's been in place for several years now, and now all of a sudden we're having problems. So we have a known good location, position A, the first tap after the head end. Let's say our trouble location here is position B, the third tap after the head end. Well, there's not a whole lot in between. If I have good signal, known good signal here at the 16 decibel tap, and I have poor signal or no signal at the 12 decibel tap, two points away from it, 150 cable feet away from it, well, there's not a lot in between. So it's either one of the 3 taps is having problems, or the cabling or connectors are having problems getting signal from point A to point B. All right, so that's a fairly straightforward troubleshooting, but knowing where the trouble location is and knowing where a known good signal level is the start of figuring out, is this going to be a quick one or is it going to be a little more challenging? Okay, now let's say that I still have the known good location at that 16 decibels tap there, the first one, but my trouble spot is way down here close to the end of the system. Now I've got 6, 7, 8 taps in between. I also have an amplifier in between, so I have a whole lot of potential failure points. Do I need to hit every potential failure point in between in order to determine what the problem is? No. I would start with looking at the actives. So look at the amplifier, right? Look at the input to the amp. Do I have good level there? Look at the output of the amp. Is it set up correctly? Is it running properly? If so, then I continue on. Then I'm going to half the distance between my known good location and my trouble location. So in this case, somewhere about the 27, maybe the 21st, 24 tap, half the distance between the known goods and the amplifier and the trouble spot, I'm gonna take a measurement there. If my signal is good there, then I half the distance again between that location. Now consider that my new known good location and my trouble location. So I'm not having to touch every single tap, but I'm isolating down where the problem might be. If at point D I do have issue, then I can back up one tap location or back up to the output of my amplifier to find out what's going on, okay? But those are just general troubleshooting practices to help quickly, easily isolate where the problems are. Again, this is for troubleshooting the RF signal And it could also be troubleshooting for too much distortion in my system. It could be for too much noise in my system. Noise and distortions are added primarily at amplifiers. So you're really going to see point A or point B would have the same noise and distortion. Only after the second amplifier would that change. But it's a similar concept. Okay. Now that run, what we were looking at is what we consider a trunk and tap system. So main trunk down the hallway, tapping off signal into different rooms, different whatever, hotel rooms, different apartments, whatever the case may be. Another type of system layout for distribution is home run, with multiple closets running where we have taps and splitters and amplifiers in the closets. The only thing between the closets and the endpoints is cabling. So all of the components are within closets. So kind of makes it easier to troubleshoot. We don't have to worry about bothering, people to get into their apartments to troubleshoot or what have you. But it entails a considerable more amount of cabling to install and finalize. I'm not going to say one's better than the other. Performance-wise, they can be about the same. It's just a matter of personal preference. So looking at a home run type system, if we're designing the system, I'm going to take and design it so that cables of similar lengths are on the same tap port. Here we have, these are 8-port taps. So where our first taps that we were looking at were an input, a single tap port, and an output. This has an input and an output, the input port here, an output to go on to another tap, but it has 8 tap ports. So it can service up to 8 rooms at a time. So here I'm breaking up the list of cabling. 50 to 125 foot, I'm going to put on a 1 tap location. Then 200 to 250 foot lengths, I'm going to put onto the other tap port. So that way I can group them together into similar length runs so that I make sure that the longest cable run and the shortest cable run on each tap get sufficient amount of signal, but not too much signal. So when designing, when calculating for these types of systems, that's what I would do, is break it up into, again, shorter runs and then longer runs onto 2 different taps so I can figure out what tap value best suits those different run lengths. Okay, so here we have the head end being the start of my system. I have an amplifier here feeding out a 4-way splitter, feeding a group of local taps, then also feeding a long run, couple long runs to other closets, where I feed a whole bunch of other cable drops. Okay, and again, same thing with these cable drops. I would group these together, write them out if you have to, and group them together so the 50s, 75s, 60s, the 35s all get grouped together onto 1 tap. And then, the 100-footers, the 100-foot range gets grouped onto another tap. The 200-foot range gets grouped onto another tap, and so on until you've used up all of your drop lengths. So in this scenario, the tap ports themselves rarely fail. They're, again, passive components. There's nothing really to go wrong with them unless some external force messes with them, like voltage getting on the line and get back feeding into a tap could cause it to fail. But other than that, the taps themselves are generally pretty hardy and not prone to failure. What can fail, what most easily fails, is connectors on the cabling. You know, due to rushed installation or just the wrong type of connector for the cable it's being put on, whatever the case may be. 9 times out of 10 issues in distribution can isolate down to connectors on cabling. So in this case here now, we've got 2 different types of cable. We have the trunk cable is RG11. That's over here, trunk cable RG11. So the longer runs, the 500 foot, the 300 foot, those are RG11 runs to minimize loss. And our drop cables, all of our drop cables going from the tap locations out to the TVs is going to be RG6. So we've got 2 different types of cable to work with, which means we've got 2 different types of connectors, different tools to put these on properly, put the connectors on properly. That's typically where, and then between these closets and the outlets, there's nothing but cable. So how does cable fail? Well, cable only fails if it's interfered with, if it's cut into, if it's not been installed correctly and it got pulled around a sharp corner and the jacket got torn or something like that. Then over time it may, or a rat gets to it and starts gnawing on it. Somebody runs a picture hanger into a wall and inadvertently hits the cable, hits the coax. I've seen it happen. External changes to the system is what primarily causes cable itself to fail. So again, as to where to take measurements, well, you've only got a limited number of locations, right? You got to figure out which drop is having problems. Is that drop tied into the MDF taps, IDF number 1 or IDF number 2 taps? Which taps is it tied into? Then come to that location and check and see if the taps themselves have good signal coming out of them, And then if they do, then it's most likely the cable itself. You have to pull another cable or something to get good signal back to that customer. But again, so that's it with home runs. Troubleshooting home runs is really not that much you can do with it, because it's just one dedicated piece of cable from each tap location out to the outlets. Okay, so that's pretty much how we do the troubleshooting, where we do measurements in distribution. In the head end itself, what we do when we set up a head end, if you have a head end with a rack full of equipment, typically we start with the highest frequency channel. The highest frequency, again, is always going to be the most difficult to balance. Because it has the most loss across coax. So we start with the highest frequency channel on our system. We're going to set it 2 decibels below the rated output of that device. So over here, I have my HDE 8C QAM DIN unit. Its rated output is plus 40 dBmV. I'm going to go directly on the output of that with my meter, and I'm going to set that highest channel. Let's assume that the highest channel on my system is coming off of this device. I'm going to set that to 38 dBmV. Now, why do I do that? So now, the next thing I come through, I'm coming through an HPC 8-port combiner. Passive device, basically, essentially an 8-port splitter with high isolation between the ports, but an 8-port splitter used backwards as a combiner. So I need to ensure that once I get through my combiner, through my 2-way splitter here, and into my amplifier, I want as flat of a signal, and also my fiber optic transmitter, I want to ensure that I have as flat of a signal as I can, all the channels at the same level. So to help account for any anomalies, any differences in loss between the ports here on my combiner, I'm going to set this 2 decibels down, the highest channel, 2 decibels down from rate, and adjust all of the other devices to that level so that I can normalize out, flatten out any discrepancy in loss among these ports without going over my rated output. I don't want to go above my rated output on any of my devices here, because then I'm adding more distortion to my system than I want to. Okay, we don't want to add more distortion than we have to our system. So 2 dB down from the highest frequency device, 2 dB down, and then come here after my combiner to measure all the other devices, all the other channels, and set them equal level. So if I'm at 38 here, 38 minus 12, well, I didn't account for the 2 dB difference here. I'm at 28 here. I should be at 26. And that's for 84 digital channels that I'm running through this system. I've got 64 channels coming out of my next gen gateway here. And I've got potentially 8 channels here, 4 channels, and 8 channels off of this guy. So I've got a potential for 84 channels coming through here, making sure they're all level set at the appropriate level here after my combiner. Then once I get everything level at the combiner, I split it to go to my main amplifier, my launch amplifier, to go out to my coaxial network at, again, 3644, the rated output of this amplifier. And notice I'm using attenuators, little inline passive attenuators or pads to adjust my levels prior to going into my amp and going into my fiber optic transmitter. Fiber optic transmitter, depending on how many physical RF channels are on the system, again, in this case, 84, needs a certain level of input. So at this point, I'm going to say it's 20 dBmV. Go into that with 20 dBmV. It's going to come out with 10 dBm of laser light for you. So again, measure the highest frequency channel, set it 2 decibels below the rated output level. After the combiner, measure all my channels, get them at the same level, adjust them so they're all at the same level, and then balance and adjust my launch amplifier output to match the specifications and or the design of the system if the designer changed what output level he wanted to run in that amplifier. So those are the positions, the places where we would measure for setting up the head end. Now, for troubleshooting a head end, let's say we've got, again, 84 channels here, and I've got issue with one channel, say. Well, the first thing I look at is adjacent channels, and I apologize, I did not write this down on my slides, but I will have it on there when I post it. Look at adjacent channels, and I look at double the frequency, or I look at half the frequency of those channel assignments. That's the first place, and 99 times out of 100, that's where your interference, your issues are going to come from. Adjacent channels, so for channel 3, I look at channels 2 and 4, and then double the frequency or half the frequency. And yeah, you'll have to use something like the RF REQ app, Blunter Tongue app. That's RFreak for short, and it'll tell you what the frequency of the channels are that you're working with, so you can figure out doubling and halving and what other channels you might need to look at. Okay, so that's essentially it for today's little webinar here. in talking about where we're going to take measurements. And I will now open it up to Liz. And if she has collated any questions, I will gladly field them.
Yeah, we have a couple questions, and if anybody else has questions, just put them in the Q&A box at the bottom of your screen. I did forget to say that in the beginning. I do apologize. And we'll spend the rest of the time answering them. So the first question is, after setting a system to the appropriate levels, how often should the system be rechecked and or recalibrated?
That's a good question. So I have, Blonder Tongue has at times managed cable television plants for a number of reasons, primarily for, real world testing and of some of our components. And so we did, and it's probably might have been a little overkill, but we were doing monthly maintenance checks. I know I used to work with a gentleman who worked for one of the major cable companies, and they also did monthly maintenance checks, health checks. Their head ends, well, they're a much larger company and had much more subscribers, so their head ends were their lifeblood. So they were, checking head ends daily. But as for distribution systems, other than trying to chase down issues, they would also monthly check the health at certain locations just to make sure everything is staying as it should. Preventative maintenance requires that you go out and take measurements periodically to be able to prevent an issue from happening. If you can stay on top of the system and troubleshoot and fix the problem before the customers see it, then the customers stay happy and you keep bringing in money. Now, does it have to be monthly? I would say at least every other month. Check, make a conscientious decision to check on your amplifiers and levels and make sure that everything is as it should be. Okay, I did find the button for the Q&A. So I see the second question here is why power doubling, push, pull, etc.
Yes, thank you.
So let me go back to that slide and see if I can do that. And let's go back to the amplifiers. There we go. Nope, too far. Okay. So on the amplifiers, we have, as you can see down here, a push-pull design and a power doubling design. All I'm going to say about it in today's venue is that a push-pull amplifier should never have more than 2 amplifiers in series in a system. So and it has to do with the distortions that are generated in the system, in the amplifier. A push-pull amplifier generates more distortions than a power doubling. So in this design here, these could both be push-pull amplifiers and you would not generate too much distortion in the system, right? But if I had a third or even a fourth amplifier going in this line, I would want all of them to be power doubling amplifiers to minimize the amount of distortions, to minimize the effect of poor quality signals. Okay. Next question. You mentioned that an RF amplifier without an input signal could be damaged over time. I'm an electronic bench tech and I have never heard of this. Can you elaborate on how such damage can occur on a solid state amplifier? Thanks. I will answer that. I do have it written down from our engineers on that at my desk. I'm working from home today, so I will answer that aside and email that out. Next question, should unused inputs on a passive combiner be terminated? Yes, I recommend terminating all ports, all unused ports, as long as they're terminated and torqued down, not just terminated loosely, so that they could potentially become an antenna for picking up signal. But yes, the short answer is yes, all unused ports should be terminated. Okay, the next question, given high output level minus gain equals minimum input level, if your input is too high, you'll be overdriving the amp. How close to high output minus gain should you be? We say in our full seminars that the minimum input, again, is the high output minus gain is the low. So for these 30 dB gain amps, will be 14. If you go more than 2 dB above that, because 3 dB is a doubling of power, so if you go more than 2 dB above that, it is recommended to use attenuators to bring that signal back down. So the range for the input to the amp should be 14 to 16 for the 30 dB gain, or 1 to 3 for the 43 dB gain. Okay, one slide showed 6 dB at a tap and one slide showed 5 dB at wall plate. Are those for digital signals or analog? They actually could be either. And so, yeah, like this example here shows a minimum signal out of tap plus 6 dBmV. Another design may show plus 5. Typically, we design for between 5 and 15 analog at a wall plate, and digital signals run 8 to 10 dB lower than analog. So potentially 5 or 6 dB could be either digital or analog. Okay. Are there any cable TV amplifiers or other devices with AGC to adjust for temperature differences or possible overload? Yes, there are cable TV amplifiers. They're primarily what they call hardline amplifiers for outdoor use. And they're in the big extruded aluminum housings, not anything that Blonder Tongue has, but they are available on the market. In a 550 megahertz, I've had issues with channel loss, which fall in the 200 to 300 megahertz area. Not sure if this is called a suck out. So my low and high channels are fine, but there is loss in between. What are the usual culprits for this sort of thing? Yes, that is called a suck out. There is no one particular thing that I can point my finger at and say, that's what's causing your suck out. But yes, I have seen systems that fail at a specific range of frequencies. And I've had it more than once, and I've had it be different things. So I will chew on that and answer that in the email and give you my best guess as to what it's going to be. Is it considered advisable to stagger channels on ports of combiner at the head end to not be adjacent channels? Yes, it is. So I'm looking at going back to my head end drawing here, if I can get there. Come on. So inside each device here, the next gen has 32 channel cards coming out of it. It has isolated combiners inside of it. The AQT8 has an combined 8 channel output. The 4S combined 4 channel output. They all have isolated combiners inside of them to minimize interference between adjacent channels. But when you're combining externally, combining different things, it is advisable to, especially if they're single channel devices, it is advisable to run them in non-adjacent ports for adjacent channels. So if I had a bunch of, say I had channels 2 through 30 here and 31 through 60 here, whatever, I would be better off if I took this connection and moved it over physically one spot on my combiner to offer better isolation between the two outputs. Yes, that is correct. What would be done to troubleshoot on one port channel in the middle of the low-high frequency range if the channel of issue is good in the head end, but at the end of the run drops? The channels around it are of adequate levels and clean. Well, that goes back to the 200 to 300 megahertz range question, where you almost sounds like you have a suck out or a trap that's physically pulling out of one or a group of frequencies. Again, I'll answer that one in email. Can you use just power doubling amps for all amps? Absolutely. Power doubling amps are a higher quality amplifier over push-pull. They also cost a little bit more, so some systems try to minimize, have a minimal budget, so they can't quite afford to run power doubling amps everywhere. But yes, you could, absolutely. Where should terminating resistors be installed in the distribution system? Most especially, they should be installed on every splitter that has an open port, every splitter that has an open port, the combiners in the head end if they have open ports. Let me step back here. Every tap, the through port of the tap, if it is not used, must be terminated, because those are all high level locations. The tap ports themselves do not necessarily have to be terminated, but as a matter of good practice, most people do. And it's not hurting anything. It's best to do it as long as you're also cinching up, torquing up the terminators to make sure they're not loose. It's best to terminate everything. Can you damage an amplifier if it's running not connected at full output? Short answer, yes, because it's running into an open and reflecting right back on itself. I mean running at full output, but without a load. That's essentially what I just said, yes. So yes, if it's running full output with no load connected to it, it's running into an open and reflecting right back on itself. I will verify with the engineers tomorrow and talk to them about it, but I'm pretty sure that that's going to cause issue with the amplifier. Is there a specific torque for terminators in inch pounds? Yes, there is. We typically use 20 inch pound. You can search on, I know several of our distributors do sell cable television torque wrenches. I know it sounds like a silly little thing, but it's what we use. They're little 7/16 torque wrenches, typically, again, 20 inch pounds. For off-air antennas, what are typical RF levels into a pre-amplifier? Oh, that's with off-air antennas, there is no such thing as typical. I can put up an antenna and put up a second antenna 10 feet away and have levels 20 dB different. I really couldn't answer that as far as what typical levels are into a preamplifier. I will look at the spec of the preamps and tell you what they should be going into a preamplifier in an email, but I can't say what the typical levels are. Hi, Don. Experience. Common cause of suckouts I found to be a directional coupler installed backwards in the trunk. That is very possible. Very devious problem to find, but good idea to check in and out ports or correctly oriented on the trunk. That is absolutely true. Another thing I've seen for cause suckouts is staples. Somebody came through and decided to quote unquote clean up the cabling in a closet and stapled all the cables to the backboard and did so in such an efficient manner. They spaced the staples every 6 to 8 inches, and in doing so, created a perfect filter to suck out a group of frequencies. So yes, I have seen the backwards tap do it, and I have seen cable staples do it as well. And I
There are a
think
couple of
that is,
questions. Sorry to interrupt.
ahead.
There are a couple questions that came in on the chat.
Okay.
We're hoping to get an answer to ideal input window for a BIDA 550-50.
Well, if you go with the math that I've mentioned on the 30 and the 43 dB amps, again, the BIDA 550-50 also has a rated output of 36 dBmB on the low side and 44 dBmB on the high. So 44 dBmB output minus 50 dB of gain puts our input level at a -6 minimum, -6 dBmB minimum on the input. That amp is rated for a -6 to about a -4 on the input.
Other questions. Carl Zook says, interested in talking to someone about combing antennas for deep fringe reception and ask about your preferred techniques. Bring in those stations that everybody wants, but no one can see directly. I'm wondering if that's more of a group question than something for Wes.
Yeah, I'll have to look at that offline and answer that one, I think.
Okay, I think we've answered some of these other questions. There are, oh, it should be combining. Interested in combining antennas for deep fringe reception. Thank you. Alexander says he can help with the suck out issue. I don't know how to share attendee information with each other. I don't think that's something I'm technically allowed to do. But if you want to email me directly, I can put it on our website as a part of our blog and part of our frequently asked questions. I do appreciate you wanting to help. Thank you very much. There's one more question. Can you talk about the difference between a standard splitter and a power pass splitter? I have found some power pass splitters in my system that would normally be a standard splitter.
Power passing splitters are typically used in the satellite environment or in an outdoor environment where you're running voltage across the coax. For satellite systems, you run voltage across the coax to power up LNBs. And in an outdoor plant type system, you run voltage to power up amplifiers that are out hanging on a telephone pole somewhere. Both of those require voltage to run across the coax. The performance of a power passing splitter versus a non-power passing or a standard splitter is about the same. There may be just a little bit more loss on a power passing splitter because of the other components that are in there to allow the power to pass through. But other than that, it's pretty much the same.
Okay. Thank you, Wes, and thank you to all for attending our webinar with us. We will have the presentation and the video recording of this presentation on our website by end of day today, first thing in the morning. And you will also get an email with both of them on for you probably by the end of day today, again, first thing in the morning. You can always reach out to Blonder Tongue through our website or through the emails that you've been getting from me with any of the questions that you have. If you have any recommendations for other topics you want to learn about, we're all ears and we'd love to work with you and get those done. So thank you again, and I hope you all have a great day.
Thank you all.